Okay, good. So, last time what did we do? We did two very important things. We did the Ginsberg criterion. And that basically says that you define something which is, that object, which is basically an integral of the order parameter over some region, some volume of size, of linear size. And then what you want is you want this guy, the connected part, to be much, much less than the average of the thing itself, squared. And when we applied the Ginsberg-Landau theory to this, we found that this implies this can only happen if d is bigger than 4. So for d less than 4, it doesn't happen, and that tells you, actually you can do it in a bit more sophisticated way. Okay, so you can put in all the constants here, and if you have a way of estimating what are the things, so remember I told you that r was basically some constant times t minus tc, right? If you have some idea what that constant is, okay? And if you have some idea what the other constants are that come into the Ginsberg-Landau action, you can do a little bit better than this, and you can tell how close you have to be to tc before the Ginsberg-Landau theory stops working. Okay? In fact, this was the original motivation for the Ginsberg criterion, because Ginsberg was trying to work with the superconducting transition, okay, the superconductor normal metal transition, and there he wanted to find out how close you could go and still apply mean field theory. It turns out that if you have a good metal and something like lead, and it becomes superconducting at a pretty low temperature, like I don't know, 15 Kelvin or something, or maybe just 5 Kelvin, I don't know what lead becomes superconducting at. But whatever it is, it's a pretty small temperature, and given all the constants, it turns out you have to go within 10 to the minus 4 or 10 to the minus 5 Kelvin to see the critical fluctuations. This works really well. Okay? Mean field theory works really well for ordinary metallic superconductors. Okay, now the high TC materials are very different, and there the critical region is actually a fraction of a Kelvin. So you can actually see the non-Ginsberg-Landau behavior in a high TC superconductor. Alright, so that was one thing that we did. Any questions about this? Yeah?
Could you kind of give a physical intuition of the system?
Yeah.
How would it look like if it does not obey this condition? Like suppose this condition, because this condition, irrespective of the means the criterion for the mean field theory,
This condition always is satisfied.
yeah. So
For a real phase transition, it has to be always satisfied.
so if this is not satisfied, there is not a well-defined phase in the system.
That there is no phase transition in the system if this is not well defined. That is correct. So if there is really an order parameter in one phase and not an order parameter in another phase, this cannot, this always has to be satisfied. The only question you can ask is my set of critical exponents that I believe describes this phase transition, does it satisfy this inequality? Okay, it has to. If you have a good physical set of exponents, it has to satisfy this inequality. It doesn't satisfy it for the Ginsberg-Landau set of exponents. Or it satisfies it only for d bigger than 4. Or let me call mean field exponents. Okay? In fact, this is one of the inequalities that exponents have to satisfy. Okay? If you have a correct set of exponents, suppose you're doing some numerics, right? And you find some set of exponents. There's always going to be some error in the exponents, right? And you want to constrain it somehow. You can use this. Now it won't be exactly what I said, because I kind of used the mean fieldness of this whole thing throughout the derivation. But you can do a little bit better, and you can actually use exponents that are the correct exponents. And then it always is satisfied. Okay?
So for a theory, for a system, suppose the mean field theory doesn't work.
Yeah.
So for using the mean field theory, if we check if this criteria is fulfilled, we will see that no, it's not.
Correct.
But the same criteria is fulfilled if another theory we have.
So if you have a correct theory and some correct exponents,
Yes.
they have to satisfy this.
Okay.
Okay. All right. That's a good question. So it has to be satisfied
Because you are giving
for the true exponents.
some physical intuition about how the phases or the different
Yeah.
look like.
That's
So
a
that
very
I
good
wanted
point.
to understand, like, how did we
It
come?
cannot be violated. If there is a phase transition, there's no way it can be violated.
So one region of the system cannot be in any other phase than the other region of the system.
That's right. That's right. Unless you have some kind of disorder in the system, right? I mean, you can imagine something in which you have some kind of Ising model where some bonds are strong in one region and they're weak in some other region, right? The place with the strong bonds will order first. Okay, but I'm talking about a translation invariant system,
Homogeneous system.
a homogeneous system. So there's no,
So they will have the same order parameter for all the regions.
no, the entire system orders at the same temperature. Okay? That's what has to happen.
For systems where we can't define proper order parameter like still equation models.
Spin liquid transitions are, let's see, you can define some kind of order. You can define some kind of topology. It won't be a local order parameter, that is true. Okay, but there are other ways of describing those transitions. Ginsberg-Landau doesn't work for those things. Ginsberg-Landau usually works for things that have an order parameter.
And what happens at D equal to 4?
E equal to 4, like I said, this mean field is correct, but there's some logarithmic corrections to mean field. It's not exactly correct, but it's pretty good.
And then one more concern, like we were talking about the higher dimensional object, like 5, 6, 5, 8 kind of a thing.
Yeah.
So I just wanted to understand the map between what people do in QFT and talk about effective field theory with these higher objects.
Yeah.
Because here you have a physical cutoff, because this 2 pi by a is your
Yeah.
cutoff for the lambda. But for QFT, normal motivation is to write a dimension 4 object and call it the UV complete description. Now, these things, these higher power things come about when you integrate out the heavier scales in the full dimension 4 thing.
Yeah.
And then you get all kind of pedoral
Yeah.
blocks of all height. But
Yeah.
here you are starting with something which already has everything in it.
Yeah.
So how do I, there the higher powers come about after integrating out.
Yeah.
Here you are starting with these higher power things already present. So, I mean, how is that like something else is happening there and this is something else?
So,
No, it's all part of the same deal. That the answer is long. It's not a short answer. Okay, so I cannot give you the answer right now. Okay, because we don't have the technology. If I give you the answer right now, it will be about 45 minutes. And it'll involve concepts that we haven't actually covered. Okay, so let's wait for that. Or you can come to me and we'll talk about it. Okay? I would rather not talk about quantum field theory, okay, if I can avoid it. Because that makes it seem unnecessarily complicated. This is a lot simpler than what people normally study when they do quantum field theory. Okay?
Are we,
Alright.
are we going to do vicious theory or the...
No, we are not going to do BCS. BCS theory is a mean field theory.
Yeah, I mean, this is a complex...
Yeah, we're not going to do it. Okay, we're going to do something else that has a U1 order parameter. But it's a global U1. It won't be a gauged U1. Okay? Alright? Other questions?
So in the Wilsonian RJ, you said that this Q6, Q8 term is relevant for D is equal to 2 dimensions. So that
They're all relevant for D equals 2. Yeah.
so these RJ procedure, this taking the small size and integral out, will not be applicable for D is equal to 2.
No, that is also not correct. Okay? You have to be clever. So as we go on, we'll discover how to be clever about
relevant or
all
not?
these things. Hmm?
No, higher, in equal to 2, higher powers, relevant or marginal?
It all depends on which fixed point you're talking about. So when I did the Wilsonian RG for you last time, which I'm going to just review briefly again, the starting point, right, the tree level RG, I implicitly did it around the free field fixed point. The free field fixed point. Okay? It turns out there are other fixed points. And if you're clever, you sit around one of those other fixed points, and even when you go to dimension 2, you can make 5, 4, 5, 6, everything irrelevant, except for 1. And that is in fact the theory of the hyperpole. Okay? But these are very advanced questions. Okay, so let's focus on simple things. Alright. Any other simple questions? Not involving quantum field theory. You know, to tell you the truth, I was very put off by quantum field theory, because when I first learned quantum field theory, it was all about infinities. And it seemed completely bogus. Okay, and that way of teaching quantum field theory is really bad. In fact, it is bogus. Okay, that's the wrong way to teach quantum field theory. This is the correct way to teach quantum field theory. Okay, Wilsonian approach. Okay, but we can have the argument later. Okay, so now, Wilsonian argument, right? So let's very briefly review what we covered. So I said first, step in Wilsonian RG is to go from something like a square Brillouin zone to something like this, where I've thrown away all kinds of information about what is the coordination number of the lattice, what is the symmetry of the lattice, because I'm assuming that by the time I come to the critical point, all the details of the lattice structure have been all wiped out. Okay? And I'll be left with something rotationally invariant. So that's what I'm assuming. Okay? For some phase transitions, that is not true. Okay? So in those cases, you have to actually retain the directionalities of the lattice. But we will not be talking about such transitions. Let's just focus on the simple things.
Sir, I forgot that.
Yeah.
How can we approximate a Brillouin zone to a sphere with radius?
Because all the short distance details don't matter for the critical point.
Short distance?
The short distance details
Yes.
don't matter.
Okay.
So at short distances, that you know that the lattice is square.
Okay.
But as you go to long distances,
Mhm.
right, you don't actually, I mean, suppose you look at a piece of metal, you don't know whether it's a FCC lattice or a honeycomb lattice, right?
Yes.
So it's the same thing,
Okay.
okay? Then we said what we're going to do is we're going to successively integrate